Hi students, in this section we're going to be covering 5.2, which will build off of some of the vocab we saw in the previous section and start to get into some of the simpler calculations we'll see this chapter. So 5.2 is about specific heat capacity and heat transfer. So first let's figure out what is specific heat capacity. Specific heat capacity is the amount of heat required to change 1 gram of a substance by 1 degree Celsius. So essentially this is a measure of how quickly the temperature of something can change. So things that have very, very high specific heat capacities will change temperature much more slower than things that have very low specific heat capacities. So these are essentially constant values for different substances. So for example, water has its own specific heat capacity, aluminum will have a very different one, gold has a different one, etc. So specific heat capacity is represented with a C. I have seen it both as a lowercase and as a capital C, but again, it's just a constant based on the material. And since we're talking about how much heat that's going to have an energy unit is required to change 1 gram, we have a mass component, by 1 degree Celsius and a temperature component, our units will have all three of those together. So we'll typically see something that looks like this, joules per gram degree Celsius, or we might see joules per gram Kelvin. 1 degree Celsius and 1 Kelvin are equal amounts of energy. So really you could use those two interchangeably in that case. Okay, so they're not the same number, but the amount of energy in 1 Celsius degree and 1 Kelvin are equivalent. So some common ones that you'll see, you're going to see the specific heat capacity of water a lot in this chapter, and the specific heat capacity of water is 4.184 joules per gram degree Celsius, or 1 calorie per gram degree Celsius. Notice it's that lower C calorie. Okay, those are also, I believe, in your reference booklet in case you forget that they're in here. Okay, so if we just have a quick little thought question here, based on what I've said so far about specific heat capacity, I want you to take a moment, pause the video, and think about this question. Which heats up faster at the beach, the sand or the water? And what must that tell us about the specific heat capacity of those two substances? So pause the video, think about that question for a moment, and press play when you're ready to hear the solution. Okay, so here you see the comparative values. Water has a much, much higher specific heat capacity compared to sand. That is because the higher the specific heat capacity, and I should also say, I forgot to mention, specific heat capacity is typically just abbreviated specific heat. They typically cut off the capacity word. So water has a much higher specific heat than sand, and the higher that specific heat, that means the more energy you need to change something by 1 degree Celsius. So the bigger this number, the more energy you need to put in to change the temperature of the substance, essentially. So the sand always feels so much hotter to us at the beach because it has a lower specific heat capacity, meaning I need much less energy to heat up the sand. So it'll heat up really fast. It will also cool down really quickly. Whereas the water, also because there are other factors as well, like there's so much more water in the ocean, it's moving, etc. But generally speaking, because water has such a higher specific heat, it will take a lot longer to heat up, which is why the ocean often feels pretty cold, but it will also stay warmer later into the evening, as opposed to the sand getting pretty cold. So the higher the specific heat capacity, the longer a substance will take to heat up and cool down, and the lower it is, the quicker it will change temperatures. Okay, so you're going to see this specific heat capacity pop up in some equations throughout this chapter, the first of which we'll see right here. So here is our first equation, Q equals MC delta T. So I always say Q equals MC delta T. I've heard people call it the MCAT because the delta symbol sort of looks like an A, but call it whatever you wish. The point is we can use this equation to help us calculate what's going on with heat changes when we're talking about, one sample changing temperatures or having heat added to it, etc. So if we look at all of these variables, let's first make sure we know what they mean. So Q, this represents our heat, and really this is heat energy. So if that's our energy term, it needs to have some sort of energy unit. It's typically joules. You could maybe see calories as well, depending on what your units for C are. M is the mass, and that's going to be in grams. C is our specific heat capacity, which again, sometimes you'll hear it phrased just specific heat, or you'll hear specific heat capacity. And that has units of either joules per gram degree Celsius, or you might have calories per gram degree Celsius. It just kind of depends on the question. So the important thing to note is that these energy units have to match up with these units here. And then our delta T, that is our change. Anytime you see delta, that means a change in temperature. And the delta, if we're looking at a change, it's always final minus initial. So it'll be our final temperature minus our initial temperature. Okay, so if I want, I could even rewrite my equation to look like this. Q equals MC multiplied by the quantity TF minus TI. Okay, so we'll see a variety of different examples with these throughout the chapter. Couple other things to note about units and signs and so forth. Again, you do need to make sure your units match up between all of these different things you plug in. I could have Celsius here. If I had Kelvin for these, I would want that to match there as well. Notice both my masses are in grams, etc. The other thing to mention about our sign conventions is that anytime we're talking about our heat energy, sorry, let me just reset here. There we go. Anytime we're talking about our heat energy, Q, that can have a sign. So the convention is if Q is positive, that means we have an endothermic process. Whereas if Q is negative, that means we have an exothermic process. Okay, so don't worry about the bullets there. They kind of make it look like two different negative signs. So positive Q means we have an endothermic reaction or process, heat's being added to the system. If Q is negative, it means heat is being released from the system into the surroundings. In other words, it's exothermic. So let's check out some sample questions. So take a moment, read over example 5.1. I suggest pause the video for a moment, read it over, and then when you're ready to start seeing the solution, press play. Okay, so as I look at this, it says how many kilojoules of heat. So if I'm trying to solve for an energy unit here, we are essentially looking at what is Q. Okay, so we're solving for Q. How many kilojoules of heat are required to increase the temperature of 35.5 grams? As soon as I see grams, I know that that's a mass. I have some temperatures here, so we've got my final and initial. If we're starting at 23.6 and going to 434, that's the final. And then it says the specific heat of iron is this. This is our C. Okay, and then it also asks, is this process endo or exothermic? All right, so step one should always be to write your equation. So I'm going to start with Q equals MC delta T. Okay, we're solving for Q, so that's helpful. Let me fix that, it's a weird looking Q. There we go. All right, so our mass, we've got 35.5 grams. Our specific heat capacity was 0.451 joules per gram Kelvin. And then our temperatures. Now, the Celsius versus Kelvin thing, I mentioned it before. 1 degree Celsius and 1 Kelvin are equivalent amounts of energy. So since I'm going to be subtracting my Celsius temperatures anyway, I can really just substitute that Kelvin for Celsius here. If that bothers you, you're welcome to convert both of the Celsius temperatures to Kelvin and then subtract. You'll still get the same number. But if it bothers you again and you want to do that, go for it. Just as a reminder, you take your Celsius temperature and you would add 273 to get the Kelvin temperature. But if I just substitute my units there, if I then do the fact that MC delta T would be the same as MC multiplied by TF minus TI. I could then substitute in here for my delta T 434 minus 23.6 degrees Celsius. If I do a quick unit check, I see grams and grams in the top and bottom of a fraction will cancel. Celsius and Celsius will cancel, leaving us with just joules. So I'll get my answer in joules and then I'll convert it to kilojoules because the question asked for that specifically. So if I go to calculate this here, I'll see that this is going to come out to be about 6,570 joules. Now we'll talk about sig figs in a moment. And then for kilojoules, I would then take that answer, 6,570 joules, and then just do a quick metric conversion. So I know that there are 1,000 joules in 1 kilojoule. Likewise, you could say that 1 joule is 10 to the negative third kilojoules. Either will work, and we'll get our answer. Now, my answer here, I'm going to write as 6.6 kilojoules with 2 significant figures. Now, why am I doing that to 2 significant figures? Quick reminder here, when we are doing our work, I do have this subtraction here, and when we subtract, the rule is we look for the lowest number of decimal places. So 434 does not have any decimal places. So if I subtract 434 minus 23.6, I would want to round that to a whole number, which would give me 410 degrees Celsius. Then when I go to do my multiplying, I have 3 sig figs, and now 2. So 2 ends up being that limiting number. So this I would want to keep to 2 significant figures as well. So in turn, my final answer has 2 sig figs at the end. So there we are with example 5.1. Example 5.2 is similar. We're just solving for something different. This time it's asking what is the specific heat. So what's the specific heat? That's getting at what is C. If we have 3,450 joules of heat added to a 150 gram sample, and its temperature increases like we see here. It also asks, is this process endothermic or exothermic? Which I realize we forgot to answer in the last question. So if I go back to 5.1 for a moment, this particular process, if I look at this question, I can see for a couple of reasons that this particular process is endothermic. Now, how would I know? Again, some giveaways. Number 1, it says that we're increasing the temperature. So we're adding heat to the system to increase the temperature. I can see the temperature going up there. All that would tell me this is an endothermic process. So if I go back to example 5.2 now, again, we'll do some calculations and then we'll also figure out, is this process endothermic or exothermic? I can actually do the endo versus exothermic now because there are some context clues here that'll help us. It says that heat is added to the particular sample, and we also notice that the temperature is going up. So again, all this would tell me this is endothermic. If it was exothermic, we would see the temperature going down. It would talk about heat being lost, etc. But if I now go to solve, we always start with our equation, Q equals mc delta T. This time, though, we're solving for C. You could either plug into the equation and then solve, or you could rearrange the equation first. It does not matter. I like to rearrange sometimes, so I will rearrange that to this. Specific heat equals Q multiplied by m delta T, which again, delta T is the same as TF minus TI. You don't have to rearrange first. That's just a personal preference of mine because it makes the units work out nicer, I think. But your choice. So if I start plugging things in here, my Q would be my energy value. So I've got that in joules. Our mass is 150 grams. And then final minus initial. The second one would be the final temperature. The 22.5 would be the initial. So if I subtract, I've got that. Now, as far as the units go, notice that none of these units cancel out. I've got joules, grams, and degrees Celsius. That just means all 3 of them will be in our final answer. If I do a quick check for sig figs here, when I subtract, both of those have 1 decimal place. So I'll round that to 1 decimal place. Now I'm multiplying and dividing. So if I count sig figs, I've got 3, 4, and 3. 3 is the limiting value. So if I do all of my work here inside this, my specific heat capacity, so 3 sig figs, comes out to 1.73, and then my unit would be joules per gram degree Celsius. So there we are for 5.2, and again, we said this was an endothermic process. The final part of this section will give us a little bit of a preview of something called calorimetry. So all of those previous examples were essentially one object or one substance changing temperature. But what about if we have 2 objects together that are at different temperatures? We know from what we already talked about that those substances will ultimately reach thermal equilibrium. But can we track what's actually going on quantitatively during that process? And the answer is yes. We can do that using our Q equals mc delta T equation. and this concept of something called calorimetry. And the basic idea behind calorimetry is that the amount of heat, remember Q is heat, the amount of heat gained by one object is the same as the amount of heat lost by the other object. But somewhere in there we toss a negative sign. It really doesn't matter which side it's on, but we put a negative sign to ultimately show that one thing is gaining heat and one thing is losing. It's just showing that difference in heat transfer there. So this idea of calorimetry is actually a lab technique that employs that concept of the amount of heat being gained by one object being lost by another. And there are various forms of calorimetry. We're going to see some more complicated ones later in the chapter. But for now, we'll just focus on the basic or most basic type, which is this idea of a coffee cup calorimeter. So what we'll do is we're essentially going to be observing the heat transfer between two different objects based on the concept of conservation of energy, the first law of thermodynamics, that we can't gain or lose heat. It can only really change forms. So what happens is the warmer object will give up heat to the cooler object, and then we'll be able to observe what's going on. In a coffee cup calorimeter, we have some object being placed into water. So my two objects will be water and something else. And we can observe how the temperature of the water changes after the substance has been added. So while we're observing that, we'll be able to see what's going on with the maybe the specific heats or the energy transfer. We can look at a couple of different things. We talk about a coffee cup calorimeter because that styrofoam ultimately just helps insulate this and keep our heat fully being transferred between just the object and the water. So visually, it could look something like this. We might have some warm metal, in this case iron, that's been previously heated up to some warmer temperature. Then we're dropping it into water that is at a different initial temperature. Over time, those two will reach thermal equilibrium, so they're both ending at the same temperature, and we'd be able to calculate backwards to figure out all sorts of things. So if we check out a sample question, it's all going to be based on, again, this basic concept, but we can substitute both sides of our equation Q with our MC delta T. So if we substitute both sides, then it would look something like this. The mass of our object, whatever it may be, multiplied by the specific heat of our object, multiplied by the temperature change of our object is going to be equal to negative, because we have to have a negative on one side. It doesn't really matter which side, though. Not our Q. For our mass of the water, specific heat of the water, and temperature change for the water. So we'll have a lot of variables, but ultimately it's just the same as the examples we previously did, just with two different things at once. So if we check out our example here, 5.3, it says we're taking a piece of lead and we're dropping it into water. So if we keep track of all of our different things here, our two objects are lead and water. So first and foremost, the basic idea is this. It says the lead was heated to this temperature and then it was placed into water. That's initial temperature was this. So our lead is the warmer object. Our water is the cooler object. Again, it doesn't really matter which side you put the negative on as long as it's on one side. So that's kind of our basic idea. So if I start substituting in, it's going to look like this. The mass of the lead multiplied by the specific heat of the lead multiplied by the temperature change of our lead is going to be equal to all the same, but for water on the other side of the reaction. Like so. So if we start then substituting our numbers in, I see a mass for the lead. And you can check all your units here, make sure they all match. You can put them into the work, you can leave them out, it's up to you. But I have a mass of the lead in grams. I have 100 milliliters of water, but remember the density of water is 1 gram equals 1 milliliter. So that's the same as saying 100 grams of water. So the grams match up. I don't know a specific heat of the lead. That's what it's actually asking us to find. What's the specific heat of the lead? And then our temperature change. So the final temperature is going to be the same when we do these simple coffee cup calorimeter problems, because both objects are ending at the same temperature, right? That's the concept of thermal equilibrium. So the final temperature for the lead is 25.1 degrees Celsius. The original temperature was the warmer 94.1. So there's everything on that side. The other side of my equation would be my mass of my water, which was 100 grams, as we said, multiplied by the specific heat of water. It doesn't tell us specifically in the question, but we did fill it in earlier in the chapter, and it is 4.184 joules per gram degree Celsius. And then, or 1 calorie per gram degree Celsius, but we'll work with the joule version. And then our temperature change, again, the same final temperature as the lead, but initially it was at 18.7. So that's the setup. Now it's just a matter of solving. So again, we're solving for this right here. Again, we'll pay attention to our significant figures when we're doing our subtracting here. And then after that, it's all multiplication and division. So if I just do the subtracting, this would become negative 69.0, keeping 1 decimal place because they both had 1. The other side would be 6.4. So at that point, then I'm doing all multiplication and division. I've got 5 sig figs, 3 sig figs, 4, 4, and 2. 2 ends up being the lowest amount. So when I go through and solve all of this, my specific heat capacity is going to be all of this divided by this product. And assuming you plugged everything into your calculator correctly to 2 significant figures, our final answer is 0.11 joules per gram degree Celsius. So there we are. Again, this is just sort of an application of that Q equals MC delta T idea. This is a simple coffee cup calorimeter problem. We'll be seeing some more complicated ones later in the chapter. But in the meantime, if you have questions, please just reach out.